First of all, it's impossible to summarize fairly a meeting this exciting with this broad bandwidth of ideas and important new results. We're here at a critical moment in the development of the field with the advent of new observatories, JWST, the VLTI results coming in. You know, astronomy thrives when there's new data appearing of all kinds, and we are in that moment. So without further ado, let me just cut through what I saw in the conference. All errors here are due to me, certainly not to the presenters. Apologize for anyone left out. 15 minutes is a short time. So what we're trying to understand is how we get from here to here. What does this structure that theorists could write down almost from first principles? We've got a magnetosphere around the star, a dust sublimation front because of the temperature of the star, a gas-free region organized on these scales. How does that imprint itself on the populations that we are measuring? So that is the task here. It's a giant task. But there's a lot of interesting things that will come along the way. First of all, there's two edges here, sublimation radius, the co-rotation point, that really came up in the meeting here in a very important way. The innermost region, as an example here, is prone to many interesting points of physics. First of all, MRI will be inactive in most of the dense part of the disk, save for this inner region, where because the heating of the star can ionize gas up to this inner dead zone radius, we can activate instabilities that kick off the MRI instability that can warm the inner part of the disk out to 1 AU, and that can affect the structure and composition of the planets that you are forming in this zone for a while. What would that do to their composition? There are stochastic torques possibly present when the MRI kicks off. That will be a factor. And disk winds, which will be present everywhere. This beautiful picture here that Bonnie Zare emphasized in here, in one glance tells you that the magnetosphere or something has imprinted itself on the MA diagram in a fundamental way. Right? So here's our magnetosphere. For typical calculations, this may go out to 10 solar radius here. There are a lot of planets that are gathered up in here. It depends on even whether you're a multiple planet system or not. Multiple planets seem to be more prone to this than otherwise, but there is structure imposed by the magnetosphere or the dust sublimation region on these planetary distributions. That's just fundamental. You see it at a glance. Anything you see at a glance has got to be important through whatever you do. Right? There's a strong magnetosphere interaction that can regulate the spin. We were told about by Zadhuat Zhu in this symposium. So we do know there's some regulation between the spin of the stars and the exchange of angular momentum with the surrounding disk here for a while. The structure of the magnetic field of the star is very important as well. We see that there's an ordered field and a disordered one measured by the octopole, which must be responsible to driving the stellar flaring, the activity of these central stars, particularly when you're in the M-star regime. So what do edges have to do with planet formation in this inner region? Well, they can determine we're determining the inner edges of the gas and dust disk. That's what the edges are. This provides an inner boundary in the MA diagram. We just saw that. This can be prone to, depending on the spin of the star and the interaction with the inner disk, we can have stable versus unstable stellar accretion modes. We can anchor. There's been a lot of discussion in the dynamics here. This inner region serves as an anchor for perhaps the entire resonant chain for a while. Many people have talked about that in interesting conversations, discussions. The stellar spin gets regulated by the co-rotation interaction. So this edge is extremely interesting. Mengfei Sun this morning gave us a wonderful talk on characterizing the inner edge distance as a function of stellar radius, and came up with this coefficient, this power law, 0.6 to 1.1, which is the best fit for the mechanism to the sublimation inner edge. We were talking about small planets. So small planets know about that dust edge. What does that mean? Are they being obliterated if they walk through that edge, as we've heard from McMaster, or is that a mark of formation? Inside there, you're forming these planets in situ. I don't think that's true, but the data, we just have to understand this better. Connection to the A stars, we heard about that from Stephen, and small planets reside outside the sublimation region, even for this A star region. So we've uncovered something very fundamental here from these edges. Planetary, so I'm impressed at how many theorists now have got ways of understanding the radius valley. For the MR diagram now, this is a very wonderful signal. It's calling out the theoretical models to understand this. Fortunately, we have compositional information here, which may be discriminatory between the theoretical models. So I regard this as extremely hopeful. The classical models have it that this is just a photoevaporation effect of one kind of population, a hydrogen envelope on top of a rocky core. But the Byrne group, this is Remo Byrne from Byrne, put together idea that you can migrate ice-rich worlds into close to the stars by migration mechanisms, and this is what's responsible for this second peak. So you would predict steam atmospheres, and these kind of work on an icy component, true different kind of a population here, has been carried out in posters by the Aguachine, Emerson Tao, and my own student Bennett Skinner here. And here's Emerson's picture of how evaporating an ice-rich world can lead to both dry and wet planets here in this kind of a diagram. I was struck by what kind of planets are we getting here. From Jesse Christensen's talk, we have this is the distribution in temperature going up here, more massive planets. There's a turn down at a massive enough planet in Neptune's, but we don't see that feature for the super Earths. And why is that? If these are coupled, if we evaporate this to give this, why shouldn't there be a feature here? The composition of the atmosphere is all important because that's the only thing we can really reliably try to observe. So in this coupling between the structure of the planet and the atmosphere, things are controlled by the oxygen fugacity, as we learned. If you turn up oxygen, you will turn down, you'll have oxygenated species as you bring up the oxygen, and you'll disappear the species that are reduced, such as methane, etc. So in this neat diagram, we see that as you get to fugacities of this level, we could have atmospheres that are rich in hydrogen cyanide. And for astrobiology, hydrogen cyanide is the feedback molecule, the feedstock molecule for making biomolecules such as the nucleotides of RNA and DNA. So here we are, as astronomers, focusing on the origins of important biomolecules with that kind of an atmosphere. All important. The challenges in understanding the connection between a planet and the atmosphere were nicely discussed by Anjali, and I can only say that if you want to get this right, talk to a geophysicist, collaborate with them, because I don't see we have enough knowledge in an astrophysics community to do it on our own. So this is a perfect point of contact where we need to build planetary science together with exoplanet science, if we're going to even understand our JWST observations, period. Nature of Planets, Sierra Grant made this interesting point here that if you look at low versus higher mass planets, you see a complete difference in the chemistry. Hydrocarbons, very reduced chemistry in the low mass stars, very oxygenated, bright water in the solar mass systems. Therefore, these low mass star planetary systems may have carbon-rich Earths. What's that like? So there are some work by Ted Bergen being done on this, but I think that's a fundamental new concept. We really need to explore this. Now, anything you do I'm going to switch to disks now. The physics of disks is largely controlled by angular momentum evolution. whatever you propose as the mechanisms of shifting angular momentum around will play a fundamental role in almost everything you do. How planets migrate, how gaps are created, how quickly the disk evolves, turbulence levels, etc. So we've learned from observations that disks are not strongly turbulent out through 10, even 20 astronomical units in the early phases. So the classic models by which most theoretical treatments of development of protoplanetary disks evolve assumed viscous treatments. Okay, that's now largely out of the window. I claim this is a new paradigm developing in the whole theory of how we do protoplanetary disks. And this is what I see the future will be coming 10 years from now. I'm just going to toss that out there. You can say, Ralph, that's crazy, but I'll stick to my guns here because there's a lot of evidence for it already. Even to the inner part of disks, we have this wonderful data shown to us by Stephen Krauss the other day, in which VLTI observations, here's where they're worth every cent of those millions that have been sent on it to see this kind of structure in the velocity field, right close to the star. So here we have outflows throughout the whole disk. Now, how are these connected with planet formation? So first of all, accretion and migration, we have to look at a picture like this to understand how a planet in a magnetized gap with a disk wind around it is actually accreting its material, as shown in these simulations mentioned in Bai's talk the other day. So here you see the disk wind moving out of the gap, a very strong wind in the gap region, because that's where the magnetic flux is concentrated. Strong field means strong wind. Could mean strong mass loss rate, but certainly strong angular momentum transport out of the disk here. Planets migrate, and there's this really cool talk by Alexandrov that said usually we try to stop rapid migration with Lindblad torques by co-rotation torque, but in this case, Alexandrov talked about a model with Richard Nelson in which you can just stop planet migration cold by having a radiation treatment of your disk and noting that kicking off vortices, the way that works in the disk model, keeps a planet right in the middle of the gap so that it doesn't even move. That's revolutionary. What about forming planets? Okay, we've got rings, but it doesn't help us to know that a planet can form a ring if we want to form planets in rings. So there must be something else that forms the rings in which first planets form. MHD winds can sculpt the disk into these regions where magnetic flux gets concentrated into gaps, and there's a ring just outside the gap. The strong winds, therefore, are not uniform across the disk, but everywhere you see strong flux concentration, that's where you have a powerful outflow going there, taking out the angular momentum. Okay? In this nice picture in work by Suriano and Riols. You see this anti-correlation between disk density and magnetic flux strength. I would love to have a Zeeman map of a disk which would test this. Too bad ALMA can't do it. Do we see that in the winds? Yes, we do. Bacciotti, 2025 this year, ALMA observations, layered outflows from HL tau. Trace these layered shells of outflow back to the origin, and you're looking at 55, 67, 86 AU. That traces back to where the rings are. Leaky traps. Pebble accretion is a very important idea in planet formation, as we just mentioned. These traps, if you think they're perfectly sealed up the flow, you get an isolation mass, about 25 Earth masses, depending where you are on the disk. The JWST observations have now shown, quite clear, this is Paolo Pinella's work, that these traps are leaky. We have gaseous material, water, etc., in the inner disk of PDS 70, which should have been shut off. It wasn't. These traps are leaky, and here you can see her calculations indicate that the data is best fit if small grains make it through and large grains do not. That is mirrored in work here, Eve Lee and Huang et al., the same kind of results shown here. If you're more turbulent, you're going to be more leaky. Disks are not very turbulent in the wind regimes, so that may help. I'm going to end this, I have a minute yet, on a new paradigm for planet information I'm going to propose here, which is I'm just going to go through the list of things that are supported by observations and theory in our community. That is, angular momentum loss is well known in rotating jets and winds. I've been working on this for about 40 years, so I've seen many generations of simulations go by and calculations which affirm this over and over again. This is solid physics. Accretion rates are driven by the disk wind because they're carrying off disk angular momentum. Therefore, the disk does not spread as in a viscous model, but it contracts to an effective flow. Disks are therefore higher column density than you might expect in a viscous model because you're pushing stuff in. That means that you could have this quieter disk means you've got low turbulence, the dust pebble growth is encouraged. The first planetary embryos, maybe, this is the big question mark for me, do they like to occur in these MHD-produced rings? Heavy disk winds, as we've learned from Takehiro Udeda's talk, that could clear the inner part, making the way for just pure terrestrial planet formation early. Type 1 migration, that co-rotation is altered by magnetic torques. Type 2 migration, we are now opening a gap not against viscous material, but against the advective flow driven by the wind. And finally, we can screen, sorry for my handling here, we can, in Eric Gaidos' intriguing poster, he shows that the disk wind can actually screen X-ray flux from the central star, prolonging the life of a planetary disk perhaps to 20, 30 megayears. That, I've just make a little plug for a review article on much of this that will appear next week on the archive if you're at all interested. And I thank you for your attention. And I want to give a shout out to the organizers here. Please stand up.
Okay, thank you very much, Ralph. Thank you for all of you for coming. Safe travels home. Enjoy the do-it-yourself workshops or the ECR. And before that, we have, I think, coffee and goodies outside. But at least you have a break until about 4 o'clock. So, aloha.